So now we begin Unit 8, which is covering atomic structure and periodicity. Majority of this unit is going to cover material that you guys learned in first year chemistry, with a little bit of additional explanation required in answers to problems. But all in all, I think you'll find this unit pretty straightforward. So when we begin talking about atomic structure, we really want to focus on electrons. And electrons, we know, have a duality characteristic where they sometimes act like light waves and sometimes act as particles. There are some equations that you need to be able to use in this area of chemistry, and these are probably things you're going to recognize from physics if you haven't done them already. And the first is the speed of light equation right here, where the speed of light is equal to wavelength times frequency. Wavelength is indicated with this little weird looking, it's called a lambda. It's a letter from the Greek alphabet. And then you also have this little V with a hat is what I call it. It's called frequency. I know they'd use an F for that in physics, but in chemistry we use the V with the hat. So the speed of light equation is on your AP equation sheet, as well as energy being equal to Planck's constant times frequency. The Planck's constant will always be given to you. That's on the AP sheet. And then again, frequency is something you can solve for or be given to solve for energy. This portion of the equation where E is equal to Planck's constant times speed of light divided by lambda, that is not on the AP sheet, but I think knowing it helps make some problems a little bit quicker to solve, and you pretty much need to know it for physics anyway, so my suggestion to you is to go ahead and just learn that equation. It's strictly a combination of these two that you have on the AP sheet. The speed of light, you do not need to memorize. It is rounded to 3.0 times 10 to the 8 meters per second on the AP equation sheet. So just be careful. Anytime you put in a wavelength and use the speed of light, your wavelength has to be in meters. One last thing before we move on, and that is frequency. Students seem to struggle with units on frequency. Frequency refers to the number of waves that pass a point in space per second. How many waves pass, or how many cycles of the wave per second. So the units are literally seconds to the -1, or 1 over seconds. So just keep that in mind. It's always per second. So let's go ahead and use our equations to solve for some of these things. First up, we're going to calculate the frequency of light that has a wavelength of 6.7 times 10 to the -5 centimeters. I already know this is going to be a problem because I do want to use the equation C equals lambda nu, lambda frequency, and I know that my speed of light is in meters per second, so I'm going to need to convert this. So I'm going to go ahead and I'm going to erase this really quick, and I'm just going to make a little dimensional analysis setup here and convert this right away to meters. So for every 1 meter, we have 100 centimeters. And so this gives me 6.7 times 10 to the -7 meters, which makes sense because centimeters are tiny, so there's a lot of them in a meter. So now we can take that 6.7 times 10 to the -7 meters and plug it into our C equals lambda nu. Speed of light is 3.0 times 10 to the 8 meters per second, and that's equal to my wavelength of 6.7 times 10 to the -7th meters, and then my V is what I'm solving for. So when I plug all of that into my calculator, I get 4.5 times 10 to the 14th, and my unit, remember, is 1 over seconds, or per seconds. All right, next problem. Calculate the energy of a photon of orange light with a frequency of 5.0 times 10 to the 14th. All right, well, if I'm solving for energy, I'm going to use energy is equal to h times nu, or Planck's constant, times frequency. So looking at this, I'm going to solve for energy in joules, and it's going to give me, it's going to be equal to Planck's constant, which is on your AP sheet, 6.626 times 10 to the negative 34th joule times second. So when we multiply by per seconds of frequency, 5 times 10 to the 14th, you can see how seconds will cancel, and we'll end up with an answer in joules. I'm going to go with 2 sig figs here. Did I do sig figs right in the last one? Yes, I did. 2 sig figs here. We'll go with the frequency given of 3.3 times 10 to the negative 19th joules. Okay, next final little problem, and then we'll move on to talking about wavelength here, is calculate the energy of a photon of light with a wavelength. So we're going from wavelength directly to energy, so that combined equation I mentioned is going to be your best bet. So the first thing I want to do is convert this guy to meters. For every 1 meter, the way I remember nanometers, nano 9, nano 9, nano 9. So there were 1 times 10 to the 9th nanometers, giving me 4.25 times 10 to the negative 7th meters. So now I can take that, plug it into my wavelength, and solve. Okay, so we're going to plug these in. Whoops. I'm going to go ahead and move this to give myself a little more room. And when I plug in energy, it's equal to 6.26 times 10 to the negative 34th. That's joule times seconds, times the speed of light, which is 3 times 10 to the 8th meters per second. And I'm going to divide that by the wavelength I just calculated of 4.25 times 10 to the negative 7th meters. So if we look at units, just watching as they cancel, that goes, seconds go, and I have joules, and I'm looking for energy, so that looks pretty perfect. My final answer ends up being 4.42 times 10 to the negative 19th joules. So looking at waves, what you need to know, you don't necessarily need to memorize the order of everything, but it is useful for you to know that your lower energy stuff are your microwaves and your radio waves on the left side of your electromagnetic spectrum, and your UV, X-ray, and gamma rays are your most, with the visible spectrum that you know is Roy G. Biv hovering in the center. You do definitely need to know the relationship between energy and wavelength and frequency and their proportionality. So as we're going across the spectrum this direction, we see we're going from radio to gamma. If you notice the wavelength here, the length from like trough to trough or peak to peak gets shorter and shorter and shorter. So as the wavelength gets shorter, the energy gets higher and the frequency gets higher. So shorter wavelength, higher energy, larger frequency, or higher frequency, and that's this side. And your longer, slower, less energetic, lower frequency wavelengths are on the left. So definitely know your proportionality. You might see questions of which of the following has a shorter wavelength, X-rays or radio waves. So you could answer that question and say, oh, X-rays have higher energy, shorter wavelength than radio. As far as Roy G. Biv goes, that follows the same order. So it's within this same trend. So red waves are not as energetic as violet waves. Okay? Moving on. Here is a little bit of a discussion of when this all first started. electrons were studied in the hydrogen atom since there was just one electron, and it was learned that electrons would absorb energy in the guise of photons, and as they absorbed energy, they would jump up to higher energy levels, and then as they released energy, energy would be given off, they'd fall to a lower level, and in the process of falling, we'd create something called emission or line spectrums. If you look at this next set of slides, this is a very good example of the different absorption spectrum for hydrogen. Before electrons get excited, quote unquote, they have at their disposal all of this visible light. So if you look originally, before this was missing little black lines like that, this was the full visible light spectrum. Well, electrons will take some of that energy from the visible light spectrum, and depending upon the element, they're going to take different parts of the visible light spectrum. It's kind of like a fingerprint. Different elements will absorb and emit different wavelengths of light. So here you can see that these little wavelengths are the wavelengths that are absorbed when electrons and hydrogen go to higher energy levels. When those electrons fall, you can see these lines represent the emission spectrum. So this is what we see as color. When we see the color of my red shirt or his blue pants, any of that, we are seeing emission spectrum. So if you can see, whatever is absorbed, that is what's going to be eventually emitted when the electrons fall down to a lower energy level. So, which makes sense because if you see color, you have to have light, right? So I don't know if you've ever been into a super dark cave like at Natural Bridge Caverns or somewhere, Carlsbad Caverns, or where you're going deep into the earth and there's literally no light, like you can't even see your hand in front of your face. Are things colored? No. Absence of color because there's no visible light for those electrons to pull from to get excited and then to fall and emit that particular color. So it's pretty interesting stuff. So what we're going to do though is move on now more specifically to the concept of the orbital and tie it to the periodic table. You guys learned that, your middle school, orbitals are in rings. That was all kind of not true. We've learned that orbitals are actually a 3D area that we have a very high 90% probability of finding an electron. So here's a picture that represents, this is two-dimensional obviously because it's a picture, but imagine that being like a three-dimensional ball, like a tennis ball or something. This is a representative of an s orbital. You can see that it's darker in the middle, lighter on the outside. This is a probability distribution diagram, and the intensity of that color, it corresponds to the probability of finding the electron. So it makes sense that electrons are going to hover closer around the nucleus sometimes than further out. But they exist out as well, so that's why we have the gradation of color within these pictures. Here is a graphical representation that we have a higher probability of finding. If you think about this as the nucleus, this origin, you have a higher probability of finding an electron the closer you are to the nucleus. So you get used to seeing potentially different graphs that represent where you may find an orbital, either in a 3D photo or graphically, such as this. So now comes the fun stuff. I always think this is fun, but let's break down the periodic table into its levels and sublevels. So we remember that levels, these are our levels of the periodic table. This is level 1, 2, 3, 4, 5, 6, and 7. And then we had our sublevels. What sublevel really means is the type of orbital. And what were the kinds of orbitals we had, whether it was S, P, D, or F. Those should all be hopefully ringing a bell. These first column represent electrons that reside in S orbitals. These 6 right here, helium actually belongs over here for that, so consider this electron an S electron. And then we have the block of 6 here, and these are our P electrons. This is our block of 10. These are our Ds. And then down here are 14 block of F orbitals. So our sublevels are the orbital types. So what's really interesting about this is the correlation of the energy level numbers to the number of sub-levels on that energy level, which will then translate into an equation that we can figure out how many electrons are on any energy level. So let's look at this. These are your sublevels. When you have an s orbital, there's only one of them on any sublevel, right? And how many electrons can one orbital hold? 2. So you can only have 2 electrons on an s sublevel. Here we have a p sublevel. The p sublevel holds 3 different kinds of p's, px, py, pz. They're just p's in different directions. So this p sublevel can hold a total of 2, 4, 6 electrons. What's interesting, if you go look at your periodic table, how many columns are across the p block? 6. That's why. It all connects. It's all pretty amazing. If you look at any d sublevel, there's 5 different kinds. Do not memorize these shapes. You just need to know that there's 5 different d orbitals. And if each orbital can hold 2, we know that means 10 electrons exist on a d, and the block is 10 columns wide. And then here are f orbitals. We have 7 different of them, which means we can have 14 electrons. If we can have 14 electrons, lo and behold, if you look, the inner transition metals, 14 across. So again, all of this corresponds and makes sense. So just to kind of put it all together for you, let's go ahead and fill in some charts. Some of you like to see things like this. So our different kinds of sublevels, again, are S, P, D, and F. Now, not all of them exist on every energy level, and we'll talk about that. But this is just review. If we have a sublevel of S's, there's only 1 orbital. That means 2 possible electrons. If you have a sublevel of P's, that's 3 orbitals, 6 electrons. A sublevel of D's is 5 orbitals and 10 electrons, and a sublevel of F is 7 orbitals and 14 electrons. Now, this is where we tie it to the periodic table. We're only going to look at the first 4 energy levels because we really only know of 4 different sublevel types. So if you look at energy level 1 in the periodic table, there is only one kind of sublevel on level 1, and that is what sublevel? The S, right? Because you go from hydrogen to helium, that's it. So there's only 1 orbital represented, and the maximum number of electrons on the first energy level is 2. If you look at the second level and just look across, you can see you've got those S's, right, with lithium and beryllium, and then you move over and you have the P's, which are from boron to neon. So there's 2 kinds of sublevels, 2 kinds of sublevels, S and P. How many total orbitals is that? Well, that's 1s and 3 p's, so that's 4 orbitals. That means 8 electrons. So interesting, energy level 1 has 1 sublevel. Energy level 2 has 2 sublevels. Energy level 3, what do we think? Yep, it has 3 sublevels, S, P, and D. And I didn't show that on the previous slide, but remember those D's are actually in an energy level below the original energy level. I'll show you that when we get to electron configuration. But energy level 3 has 3 sublevels, S, P's, and D's, and that's a total of 1s plus 3 p's plus 5 d's, that's 9 orbitals, and that is 18 electrons you can put on the 3rd energy level. And on the 4th energy level, 4 sublevels, shocker. So what are our 4 sublevels that have the energy level 4? S, P, D, and F all exist on the 4th energy level. That's a total of 9 plus an additional 7, that's 16 orbitals. That makes 32 electrons. So if we want to relate each column here to the energy level, where N stands for energy level, that's a pretty common abbreviation. If we want to, using N as our variable, what is the number of sublevels on any level? It's the same as the energy level, right? 1, 1, 2, 2, 3, 3, 4, 4. What about orbitals? What if I wanted to know, do you see a relationship between energy level and orbitals? Well, if you look, it's actually N squared. If I square 1, I get 1. If I square 2, I get 4. If I square 3, I get 9. If I square 4, I get 16. So the number of orbitals on any energy level is the energy level squared. And then I just need to multiply that by 2 to tell me how many electrons. So 2n squares tells me how many electrons are on an energy level. That is a really important little equation to know. It's important because you might be given some theoretical level, like level 27, that's not on the periodic table yet, hasn't been discovered. But based on the fact that all of this is quantum theory and based on a formula, we can extrapolate kind of and utilize that n and square 27 and multiply it by 2 and figure out how many electrons are on this theoretical energy level. All right, so let's try some of these questions. What is the maximum number of electrons in a 2s sublevel? Well, there's only one orbital on an s sublevel, and it's a sphere, and it only holds 2 electrons. So going across, in a 3d sublevel, ooh, how many orbitals are in the d's? 5. So what's my total number of electrons? 10. Now, we want to know how many electrons on an n equals 4. I don't want you to sit there and on your fingers count, oh, I have S, P, D, F. No, use the formula, 2n squared. 2n squared tells you how many number of electrons are any one energy level. So if you put the 4 in, 4 squared is 16 times 2 is 32. That's going to be your fastest way to do it, because they will often ask you, oh, energy level 5, energy level 6. And there's orbitals we don't know about yet, like G's and H's, a theoretical next orbital. So you have to use the formula sometimes. And then finally, 2p orbital. This always throws students off. A lot of students go, oh, p has 3, that's 6. Whoa, no. It says AP orbital. They're not saying all 3. It's not saying a 2p sub-level. It's just saying a 2p orbital. So one of those 3 dumbbell-looking things is a 2p orbital, and it only holds 2 electrons. All right. Well, that's it for this little lesson. Be sure to go do your homework and practice with your sublevels and the verbiage associated with electrons, orbitals, and sublevels.